All right, so those of you that have been about to fall asleep, or for the invisible members of class, at least get a chance to watch it again. Let's share. All right, so in theory, everything's all happy. And we will continue with fluid statics and pressure. So a quick outline, fluid statics. We'll introduce you what pressure is, although you've heard the musical rendition of it, which is every bit as good as the real thing. How pressure is measured, and just a little bit of introduction to that. And then we'll start with hydrostatic forces on a plane surface, something that's submerged. We won't complete that today. We'll complete that next time. So what is fluid statics? That's CE-3301 all over again, except with fluids instead of rigid materials. It deals with forces in fluids that have no relative motion within the fluid. So an example would be a very well balanced coffee cup if you're not shaking around. So the coffee at the top of the cup. So the energy drink at the top of the can and the bottom of the can aren't really moving relative to one. We just screwed it up. Thank you very much. So that the fluid within the vessel has no relative motion. And that, in many instances, is a fairly realistic approximation that's useful. There are two principal types of forces that we are involved in: body forces and surface forces. Body forces are forces that are spread throughout the body, and surface forces are the forces that your pet produces on you when it tries to make bread out of your body. So you can get them both together. So body forces are things that are distributed throughout the volume. So imagine this big beach ball made out of water. It's been outdoors there for a while, so it's a big old solid beach ball. It's just wrong for it to be 20 degrees Fahrenheit, no snow on the ground. That's criminal. Its weight is a body force. It's distributed uniformly throughout the body of the object. The surface forces would be you holding it up. So if the sphere was the Earth and you're holding it up with your shoulders, you would be known as, very good, thank you. Thanks for playing along. Those are examples of surface forces. So they occur at contact points. So that implies this idea of boundary contact. You've had all this before in solid mechanics or statics or whatever it's called nowadays. So our sphere right there, we've drawn a rectangular region. I think it's supposed to be square, but looks kind of distorted. And we've introduced two arbitrary axes that are tangential to that small little surface. One's labeled X, because that marks the spot. The other one's labeled Y. Why not? And there's a third one coming out perpendicular to those first two called, I know it's Z, but I have to show Z, otherwise it just makes the video long. It's the Z axis coming out of it. So those are supposed to indicate an orthogonal three-dimensional coordinate system. So X kind of going that way. And for those of you listening to the recording, I'm kind of pointing that way. Y pointing sort of this way, and Z is pointing out of the bubble. So if you were an arrow trying to pierce that bubble, the most perpendicular contact point you could achieve would be to put your pointy part of your arrowness along the negative Z axis and plunge into the bubble until all the bubble guts comes spewing out. But if it's outdoors right now, it's just going to kind of ooze out because it's real cold. And this small rectangular area has an area associated with it. And there is a vector there labeled dA, which does not stand for district attorney in this case, but it just stands for the differential or the infinitesimal area. And there is a shear force vector in the tangential direction in this particular drawing, coincidentally going in the X direction, but it could be arbitrary. So it could have some Y component in the real case, or as real a case as I can draw. And then there is a force vector pointing in, like that arrow that was going to pierce it. And that's labeled in this case dF sub n. So it's a normal force, normal because it's perpendicular to the plane of study. Okay, so why did I go through all that other than to waste a minute of your life that you'll never get back? We're going to use that to talk about contact forces and pressure. If we were to take the force, either the normal force pointing in or that tangential force, and divide by that infinitesimal area dA, the result of that division is a stress. If it's the normal force, what kind of stress is it called? Easy question. Take the word normal from normal force and the word stress from stress, join them together, throw the force out, you have normal stress, also known as a pressure. If it's the tangential force, the F sub tau, the type of stress it is a shear stress. Tangential stress will work, but shear is what I'm looking for. So our usual notation is sigma is the limit as the area vanishes of the normal force divided by area, and tau, the shear, is the limit as the area vanishes of the tangential force divided by the area. And at this point, it's convenient to invisibilize the bubble, if that is a word. It is now, I just invented it. And we can look at the various stresses that occur on the plane of that small area. And here we have a shear stress that's going in the y-axis direction. Here's a shear stress in the x-axis direction. And here's the normal stress in the z-axis direction. And you notice there's a double subscript notation that was invented by mathematicians as job security for everybody in this building. Apparently times are tough because they're still writing with rock on rock. And it's a tensor notation, and the usual convention is that the first subscript indicates the direction of the outward pointing normal vector to that little plane, and the second subscript is the direction that the force is applied in. So if we were to write those three stresses that are depicted on the picture that I just disappeared from your vision, we have sigma ZZ is a pressure force, tau ZX and tau ZY are the X and Y components of shear, respectively. So fluid pressure, its usual symbol is P, is the normal stress applied to a fluid element. So in practice, we typically just make a direct substitution. We drop the sigma because we want to save that for other things like surface tension and standard deviation. There's just been a big argument between the statisticians and these other mathematicians of which letter of the Greek alphabet they lay claim to. Like our alphabet, only having 20 some odd letters to work with is kind of a limit when it comes to arguing over what letters mean. It turns out if you put a bunch of them in a row, you get a word, and you can make it mean whatever you need. So pressure is a normal force per unit area, and at any point in the fluid, it's a scalar quantity. Pressure is an unusual force in that we will go ahead and demonstrate that it doesn't convey much in sense of direction on its own. So the pressure right here where my finger's pointing, and if I were to move my finger over the other side of the room, I'm not going to walk because I will trip most likely. I know what the pressure is here, but it's acting either in no directions or all directions at once. It has to have something to act on before it will get any sense of direction. The other two stresses, the shear stress in X and Y, do have direction. The dimensionality of pressure is force per unit area. Typical units are newtons per meter squared, which is also known as a Pascal, or pounds per square inch, which doesn't have another name. And pressure is also expressed in some other units, atmospheres, which is 101,325 pascals, or 101.325 kilopascals. So Pascal cloaks over that, 150 years ago. Or 14.7 pounds per square inch, or 10 meters of water, equivalent depth, or 29.92 inches of mercury, equivalent depth. And there's probably a few more common measures of pressure. Back when I was sitting in the seat you're sitting in a different part of the world, but the same conceptual thing, we had to memorize all that garbage. And it doesn't leave your head. The human memory is amazing. The more useless the bit of information, the more persistent it is in the memory. So its standard atmosphere is 101.325 kilopascals, or 14.7 pounds per square inch, or actually it's a little bit more than 10 meters of water, or 29.92 inches of mercury, or 33 point something feet of water. You memorize it and you never forget it. You guys have the advantage that as long as the internet is working, you don't have to memorize as much stuff, which in theory is good, but we use the increased random access memory that's now been freed up for other useless garbage. Just remember 35 years from now, if you remember something from today, it was probably utterly useless. The useful stuff you'll forget quite quickly. So let's go ahead and demonstrate the pressures of scalar. The force that it causes, once pressure pushes on something, that force has direction. So that is a vector. Come on, shrink a little bit. Now my fancy Apple computer is supposed to do that when I make those movements with my fingers. Okay, well, it's not going to play. So imagine, if you will, we have a wedge of static fluid. Let's use this room, for instance, as our fluid, and we take some wedge somewhere in the atmosphere here. And the variation in pressure between the floor and the ceiling is not very big in this room. You have to go up several thousand feet before you get a significant variation in pressure. You go up about 20,000 of those feet, we would all have difficulty staying awake because there's not enough oxygen there to keep our brains working. And as I'm breathing the oxygen in this room, we're getting to that effect. So here's our wedge. We have this one face that's cut at an angle. The angle it forms of the vertical is alpha. We chose alpha. Why? Because it looks like a fish, and where a fish found? In fluids. So that's why the angles are alpha. Thank you for grinning at my crummy pun. And here's our outward pointing area vector for this particular plane right here. We have this triangle on the front. That's our front face. We have a parallel triangle behind it. That's the rear face. We have this rectangle, which is the right face, and this rectangle down here, which is the bottom face. And the other angles are labeled. The length of this side is delta L. This one's delta X, and that one's delta Y. And they're all drawn different lengths just to confuse the heck out of you. Hopefully that was successful. If we were to express delta Z, the change of the height in terms of this plane right here, delta Z happens to be equal to delta L times the sine of fish. And delta Y similarly is delta L times the cosine of alpha. When I said fish before, I meant alpha. So there's our free body diagram of a small wedge of fluid. So if we analyze that, aren't you glad I'm not writing this on the chalkboard right now? Yeah, me too. If we were to analyze that wedge, we can demonstrate that pressure is a scalar. And what we're really doing is implementing Pascal's law. Who remembers who Pascal was? Don't they do any like history of famous scientists in the other classes? Well, he was, I'm pretty sure he was a geek. He was hanging out back in the day, thinking about stuff like this. And if I had prepped my stand-up comedy better, Blaise Pascal, he actually was more into gambling than physics, but he did a little physics on the side. So he, in addition to these physics laws, he has some very interesting gambling rules. They probably wouldn't let him in a casino in Las Vegas today. So let's do a force balance on our little wedge. Remember from statics class, in your force balances that you always said the sum of the forces is equal to 0. Then you drew arrows every which way in that and wrote down every letter of the alphabet that you could and hope you get partial credit. But we're going to do that again here. So the sum of the forces in the x direction, we'll set it equal to 0, and we will take the pressure force on the back face minus the pressure force on the front face equal to 0, and we will learn the startling discovery using the double subscripting that pxx is equal to pxx. Amazing, isn't it? 1 equals 1. We do the same thing for y. Now, in the y direction, we have some component of that angulated deal. So we have pyy delta x delta z plus the normal component, p sub n, delta L sine alpha x is equal to 0. And when we get done with the analysis and zero out everything that we can, we discover that pyy, the force in the y direction, so pyy is this force here, is strangely equal to p sub n, the normal force. Now, the only way that can actually be true is that force has no vector quantity to it. Play the same game again in the z, and in z we have to actually consider the weight of the little wedge. Notice we immediately use pressure to compute forces, and we apply trigonometry to the red wedge and resolve the force components. The various directions are associated with the outward pointing normal vectors associated with each of the planes. When we complete the analysis, we get figure 39, which is coming up on the guitar right now. So the z component of pressure minus the normal component minus the gravitational component is equal to 0. Take the limit as the thing gets really teeny, and we discover that the z component is also equal to the normal force, or to the p sub n, the one that's on the angulated part. And finally, we put everything together and we discover that p sub n is equal to pyy is equal to pzz is equal to pxx, because the orientation is all arbitrary. And the only way that can be true is that that has to be a scalar. So there's no direction information carried by the pressure. Now, once we have an area is what carries the direction. So your body can withstand enormous pressures as long as you have no surface area. It can be fine. There is practical application of that law in that a closed system, the change in pressure is transmitted undiminished throughout the entire system. And that's a phenomenon that makes hydraulic machinery work. If you look at page 49 of your current textbook, don't do it now. You probably don't even have it with you. Some of you probably don't even have one. That's fine. You can try to get through this without buying one. That's cool. I didn't say that. I was just lying on the recording. So we're just making that up. But in page 49 of Hibbler, there's an example of a hydraulic jack lifting a car. And the reason that works is this Pascal's law. So if Pascal's law were to be repealed, we put a whole lot of auto mechanics in a difficult situation because their hydraulic jacks would no longer work, and they would have to go to some more mechanical object, such as pulleys and galley slaves. And galley slaves are hard to come by nowadays. Every restaurant in the country is complaining how they can't get galley slaves right now. Even if we pay them enough, they won't show up to work. So who's worked in food service ever? Yeah, if you have a choice, would you do something else for money? Yeah. Yeah, I was the best Hobart repairman at the restaurant I worked at. I saved them a fortune of actually having to get qualified repairmen for it. I don't want to do that again. You know what Hobart is? Yeah. Did yours break a lot where you worked? Ours broke all the time. I mean, it was the most breakingest piece of equipment I'd ever been exposed to until I had my own car. So we expressed pressure in a couple of ways. One is absolute, the other one is gauge pressure. There's nothing particularly special about either of them. You would have to be aware in a particular problem case of which one's being reported, because it does kind of matter in that sense. So pressure is usually measured against a reference value. The two values in common use for measuring pressure are a vacuum, or a real vacuum, which is considered zero pressure. Now those are hard to find in this universe. If you were to leave the Earth in one of Elon Musk's go-fast rocket ships, and fly as far away from astronomical bodies as you could find. So there is a part of the universe called the middle of nowhere. It kind of resembles Brownfield, Texas, with less buildings. Okay, so if you get out there and you get your pressure out, it turns out that you find 3 or 4 molecules of hydrogen, probably some carbon. It's not zero pressure. It's pretty darn close to zero pressure. If you don't put your helmet on, you're going to have a hard time breathing. But that's what's meant by a perfect vacuum. They do not exist, although I think you can get pretty close to them with turbo vacuum pumps. So that is absolute pressure. So you have zero vacuum is a reference pressure, and then if you measure all pressures against that zero, that measurement is called an absolute pressure. So for instance, if we had the ability to get to zero pressure on the surface of the Earth, we would find out that the difference between zero and the atmosphere is about 101.325 kilopascals, give or take a pascal. The other way to measure pressure is against a different reference. A convenient reference for measuring pressure is that very atmosphere. So if we measure differences between the atmosphere and some pressure, that's called a gauge pressure. We don't have to use the atmosphere as a reference, although that's probably the most common. So gauge pressure sometimes we thought of as a differential pressure between a reference and whatever you're measuring. Gauge pressures can become negative. So if you see a pressure reported and it's negative pressure, it's pretty unlikely that it's an absolute pressure, because if we can't even get to zero in the universe, getting to less than zero is going to be really hard. They haven't even made bad movies about that yet. Although I think the next movie involving black holes, they'll get to negative pressures, because I just told them that. So here is a cartoon to try to indicate those various references. So here's our zero absolute. And if we measured a pressure and reported it as 0 pascals absolute, which is one way of writing it, or 0 psi, pounds per square inch absolute, that's how you report an absolute pressure. If we went up to 51 kilopascals, we could report that as 51 kilopascals absolute, or minus 50 kilopascals gauge, assuming atmospheres are standard. We get up to 1 atmosphere, we're at about 101.325 kilopascals absolute, 0 pascals gauge, 0 psi gauge. Notice that the letter of the alphabet changed from an A to a G. And then moving up greater in the pressure column, we go up to 200 kilopascals absolute, which is equivalent to 99 kilopascals gauge. And that's the difference between gauge and absolute pressure. Most pressures you'll encounter in practice are probably gauge pressures. Absolute pressures were invented by college professors to ask you questions to give you a chance to screw up your arithmetic. That's probably not entirely true, but that was supposed to be a little bit funny. Our next tool is the hydrostatic equation. I think you probably had this in statics, so consider this review. We'll develop the fundamental equation of fluid statics, and we'll look at a couple of applications. If you don't want to listen to me, that's fine. Page 52 of the book has a summarized explanation of what I'm going to go ahead and attempt to show you. One of the two is probably better. That's your choice to make. We call it fluid statics means we have no relative motion within the fluid. The entire fluid behaves as a rigid body. So think of Jello as a working mental model. If the fluid you're interested in resembles Jello, that's a good approximation of a static fluid. As a rigid body, that means there's no angular deformation in it, which implies that there's no shear stress within the fluid, and static fluids, therefore, can only sustain pressures. Jello can do shear stress, so Jello is not a totally perfectly good model. But fluid statics means there's no relative motion. It means that that dV dy term that we talked about our last meeting in terms of the cross-film velocity profile for discussing what viscosity is, that's zero. The only way that can be zero is viscosity is a property of the material. It's that the shear has to be zero. So that makes tau equal to zero. Often, statics also means that the change in velocity with time is zero, but not always. So here is our parallelepiped fluid element. So we've gone from wedges to cubes. So we've gone from our wedge period to our cube period. Your art to throw up some of that Picasso stuff. So this is during Picasso's cubist period when he was studying fluid mechanics. And so our cube has a top, a bottom, a left, right, front, and a back. And there's arrows there, and circles in the back explaining each one. There's arrows there indicating each of the various pressures. So P sub left is pressure on the left pushing into the cube. P right is pressure on the right pushing into the cube. P top is pressure on the top pushing down on the cube. P bottom is pressure on the bottom pushing up on the cube. P back is pushing the cube towards you and then duck with the accelerate. P front is pushing it back to try to keep it from hitting your head. And right there in the middle, the little starry thing that represents the centroid of the cube, and it has a W next to it. Speculate what the W might mean. Wait, correct. And there's also a little arrow there indicating P sub zero, which is the pressure right there at the centroid. We have our XYZ coordinate system hanging out there in the lower left-hand corner. I think we got everything that you would need in a free body diagram, plus some extra. Oh, and the cube dimensions are also indicated here. So dy in this dimension, dx in the x dimension, and dz in the z dimension. And so there's our fluid element. And if we analyze the forces on that, we could go ahead and go back to our statics class. And remember that the sum of the forces is really mass times acceleration. And in statics, we just run acceleration to zero to make life easier. And the forces in this case are comprised of the body forces, which is the weight, and the surface forces, which will be the pressure forces on each of the 6 faces. We'll do it we'll put D's in front of everything so we can pretend they're little so that they don't vary across a dimension very much. And eventually we'll take limits and make everything go away. So the differential mass is simply the density of that cube multiplied by its dimension, rho dx dy dz. So recall what density was? Someone play along. I know this is a dull day, but look at the bright side. You're not out there. So delta x, delta y, delta z is what? The movie Spinal Tap. They wanted the amplifier to go to 11. What does 11 do on the Spinal Tap amplifier? It adjusts the for people, just embarrassing the hell out of yourselves. You turn the fill in the blank up to make it louder. Oh, yay, thank you. So dx, dy, dz is volume. And rho has what units typically? It's what the Pope convenes every Wednesday evening and every Sunday. Mass divided by the amplifier knob, volume, multiplied by volume. What do you get back? Mass. So mass is equal to density times volume. That's all this is saying. We'll look at the body force to get the weight. The weight is simply rho times g times the volume. Density times the gravitational acceleration times volume is the weight. And so no surprise there. And now we'll look at the surface forces. There's 6 surface forces, but 3 directions. We have the X, Y, and Z, which we're using I, J, and K, which is easy as A, B, and C, which is easy as 1, 2, 3. And if I could do a Michael Jackson imitation, a plausible one, I would have. So in the X direction, we have the pressure from the back minus the pressure from the front acting on that area, which is dy dz in this case. In the X direction, pressure on the left minus pressure on the right, dx dz. In the Y direction, pressure on the top, pressure on the bottom minus pressure on the top, acting in the Z direction, dy dz. And we don't know the magnitudes of the pressures yet. That's irrelevant. I've chosen the back, front, left, right, bottom, top to be coincident with the coordinate directions if back, left, and bottom are bigger than the respective front, right, and top. So we write the surface and body forces of the element and equate them to acceleration. If we expand the individual terms about that centroid, we note that we have partial derivatives. We can write that the pressure force on the back is whatever it is at the centroid minus the variation of pressure with respect to position in the X direction multiplied by dx over 2. Because the centroid's in the middle, so we're going half the distance to the left wall, half the distance to the right wall, half the distance top, half the distance bottom. So we do that 5 more times. Aren't you glad I'm not writing that on the board right now? Yeah, me too. Recall from calculus, so we collect everything together. And if we look at the terms in the parentheses, these curly parentheses, as we write each of those forces out, and then here's the various areas, everything in the curly brackets is actually a gradient of pressure. So wanting to be compact in our writing, we'll go ahead and just state that it's the gradient of pressure times dy dx dz is equal to the sum of the surface forces. And so the surface forces can be replaced as the negative of the pressure gradient times the volume. Finally, we put the body force and the surface force together and substitute into the same force balance equation, divide by the volume, and what we have left is rho g minus the gradient of pressure equals rho times acceleration for a rigid body. So that is a fundamental equation of fluid status. One common value of acceleration that's popular among people that study this is the acceleration 0. 0 is popular in almost anything involving multiplication because it makes stuff go away. So if we were to invoke the special case of acceleration 0, we have that the body force minus the pressure gradient equals 0, and that is the hydrostatic equation of a fluid. If we break it into its components, we have the X, Y, and Z components. Usually, what direction do we associate gravity with? In the Cartesian system, usually we make it as Z downward. So if we make the gravitational vector minus G in the Z direction, we can make those substitution, and we come up with these last 2 expressions, which are actually not necessarily practically important, but intellectually they're pretty important. The first one says that the change in pressure with respect to X is equal to the change in pressure with respect to Y is equal to 0. That means that any elevation of fluid perpendicular to the gravity direction, pressure doesn't change. It means that the pressure right here, basically my nose height from the floor, is the same as the pressure in that corner of the room, my nose height to the floor, assuming the floor is reasonably level. And as you all know, as good civil engineers, everything we construct is reasonably level. Not. So in any particular plane, X, Y plane, at a particular elevation, so Z is equal to some constant, the pressure doesn't change. if the elevation's held constant. That's kind of a handy bit of information. The other statement is that the change in pressure with change in elevation is equal to the negative of the specific weight of the fluid in which we're changing, or minus gamma. So to put that in more practical terms, imagine this room was instantaneously filled with water, but we knew it was coming long enough to hold our breath. So everyone take a deep breath and hold it. Excellent. So we're 8 feet below the surface of the water right now. We would experience the feeling of pressure on our ears, unless you're really bad at holding your breath or you've never done that, until we bob up to the surface and then like little birds trying to get air, because we can't do that collectively for very long. Guessing you guys are young and pretty fit, so you got 3.5 minutes down here on the floor. I'll be dead in a minute and 10 seconds. I'll be unconscious probably pretty close to them too. So let's not do that other than a thought experiment. So when you go down in a swimming pool, anyone's ever done that? Your ears feel like stuff's pushing on it because the pressure inside you is roughly 1 atmosphere. And the pressure when you go, they don't make 30-foot deep pools. All you Olympic caliber divers, what's the depth of a diving pool? Is it anywhere close to 30 feet deep? 15, yes. So half an atmosphere down is the best you can do. But you know you're down there at the time. I mean, in addition to not being able to breathe all the atmosphere around you because your gills haven't formed yet. And that is, you are experiencing hydrostatic increase of pressure as you move down in the fluid. And when you come back up in the fluid, the pressure decreases back into your inside body cavity pressure and the outside air pressure are the same. If you're a scuba diver and you make the mistake of going down to say 90 feet, getting a good lungful of your scuba air, you are inhaling it at pressure that's equivalent to the outside pressure. So you're at 3 atmospheres. And then they teach you in scuba school, if you get scared that you want to go up really, really fast, that's a lie, because you will come up really fast. And fortunately, the human body has a special adaptive technique. Instead of just blowing up because you have 3 times the pressure, all the gas bubbles into your blood and it gets in your joints, and you get a very painful condition, affectionately known as bed sleep. Pain. You got bed. Yeah, I think we're done for the day. Let's go drinking. That was my solution the one time. I had my weight belt. It came off. This was back in the olden days. The technology has improved greatly since then. So we were diving a kelp bed, and the easiest way to get through a kelp bed and hopefully not get eaten by a shark was to kind of rotate as you're swimming through. We had these old clasp belts, and my clasp caught on a piece of kelp, ditched itself, and then all of a sudden I'm wondering why I'm on the surface. And burning air, trying to swim back down again, and then finally gave up and went to shore, and I felt like crap. So our solution as 20-year-olds, so you just got the bend, you probably should seek out medical care. We went to the nearest bar and called it a day. So I'm still alive. We had many great dives after that. We were done for that day. We had the good sense to quit. So if you ever experience rapid ascent after a lungful of scuba air, call it a day. You're done. I guess if it's really desperate, I'm told that you could drag your person back down under there and hold them at 10 feet for as much as you can control them, but that's pretty desperate. It's best to go get medical attention. Hopefully you're near a big city that has a bariatric chamber that can take you back. But it's better to be good. Okay, so that's what hydrostatic pressure is all about. So you've got much fluids today, but you get really good at your stories. So back to the, make sure I'm in the right place. That was the wrong one. Yeah, we're in the right place. So here is a diagram on the right is more useful than the wordage on the left. So in this diagram on the right, this is our up-down axis. here's our water level. Here's the surface of the harbor in Catalina Island in Southern California. 90 feet is a boat called the Subic. Has this really cool moray eel in the back end of the boat, comes out, jumps out at you. You don't want to get bit by a moray eel. 90 feet is beyond your regular dive tables that you're supposed to train. So you basically do what's called bouncing. You got about 2 minutes at 90 feet and you work your way back up. So as we're going down, our pressure is increasing. So we get to whatever our depth is. And that is the pressure we experience. In this case, P sub Z versus P sub Z. And then if we move back up, we follow the slope of that line. This axis is representing pressure. There's a little bit of calculus to show you how to calculate it. Normally, it's pretty straightforward. Pressure goes up when you go down in the fluid. It goes down when you go up in the fluid. And presumably, you know where the free surface is. And the pressure at the free surface is 0 gauge. So if Z in that picture happens to be 10 meters, pressure at 0 is 1 atmosphere. If we go down 10 meters into that fluid, and that fluid happens to be water, what is the pressure at Z equals 10 meters? Z0 is 0 gauge, so 0 atmosphere. Z minus Z0 is minus 10 meters. So we have a minus 10 right here. We have a minus rho G there. So we have 10 times rho G is equal to the pressure at 10 meters. Numerically, that happens to be roughly 1 atmosphere, or 14.7 psi, 101.325 kilopascals, or 1 atmosphere. All 3 units are completely appropriate. That was for incompressible fluids. If we go to compressible stuff, we have to invoke equation of state. So if we're in the atmosphere, pressure is no longer, rho, the density is no longer a constant. It's changing with localized pressure and temperature. So we have P is equal to rho times RT. We can put that into the expression, and our equation looks quite a bit different. It says that P at depth is equal to our reference pressure times E, which is the second vowel in the alphabet, minus G over RT times whatever the elevation change is. Occasionally we'll use that, figuring out what the pressure is if we go from sea level to, say, 5,000 feet elevation. I can't do that in my head. I don't actually know. It's a half of PSI. I think it's half PSI per 1,000 feet. So if you go 5,000 feet, you're going to drop 2.5 PSI. So the pressure in Denver right now is, let's call it 15 PSI right here. So the pressure in Denver right now is 12.5 PSI. So if you were boiling water, where would it take longer to boil? Well, we're at 3,000 feet. All that stuff's off. Houston to Denver. Okay, so if you're boiling water in Houston, you turn the fire on. What temperature is the water going to boil at Houston? You're at sea level. 212 degrees, that's Fahrenheit. What would it be in Celsius? About 100. You go to Denver, so we're at 12.5 pounds per square inch. What's just changed there? The vapor pressure. So we go ahead and turn on the fire. The water starts to boil. Is it going to boil at 212 degrees or less or more? Less, you're correct. It'll boil less because the vapor pressure, the pressure required for the water change phase is slightly lower because there's less atmosphere pushing back on it. And that actually has a consequence if you're doing stuff like cooking food, but that would imply that you're actually following a recipe. If you're microwaving it, you just add a few more seconds on the microwave. Frozen burrito, 222 at sea level. You do 222 and then do the plus 30 in Denver. And you have a heated burrito. You're laughing, you've done that. So what do you all live on for food as college students nowadays? We lived on burritos. They were the greatest invention of chemical engineering in the 1970s. First, they had the microwave made by Amana, the radar range, and then you get frozen burritos. They were like 27 cents each. So you get a 12-pack of Lucky beer and a burrito for a couple of dollars. And that was back when the economy was good. So burritos and beer, not a good way to go through life, but it's okay for a couple years. You didn't answer my question. What do y'all live on? Oh, so your beans and rice. What about the rest of you? Tortillas, chickens? Rice and chicken every day. Who does beans and rice with egg on top? Gallo pinto. So it's the national food of Costa Rica. They serve it for every meal. It'll keep you from dying, but it gets old after about a week. Beans and rice for breakfast was really creepy. But someone else was cooking, so I just ate it. Shut up. All right, so let's get back to fluids. How do we measure pressure? One way would be to go to YouTube and select an appropriate rock and roll singer to hear their cover of pressure. Another way is a barometer. That's a tool for measuring atmospheric pressure. It looks like I have a cartoon of one coming up in the guitar shortly. Another one is a piezometer, a manometer, and then there's Bourdon type gauges, which actually doesn't necessarily measure pressure, but it's an instrument that produces a readout of pressure. I'll go ahead and take the link so that you can see them. And you'll notice in the upper left-hand corner, Bourdon is not only a name of a device, it happens to be a name of the company that sells these gauges. Inside, there is a C-shaped tube of very precise geometry. And as the applied pressure changes, that tube expands and contracts a little bit. There's a bunch of gearing in there. It used to be made by Swiss watchmakers. I think it's now made in Asia somewhere because they can do it better, cheaper, or at least cheaper. The principle of operation, hopefully this has the drawing. Come on. So we're not going to read the peer-reviewed journal publication on how it works. This tube is filled with gas and the pressure is allowed to come in, and as the pressure changes, the force on that tube changes. If the force changes, the tube is going to change shape slightly. It doesn't have to move much because it has all this elaborate gearing here that's represented by this wiggly thing and this little gear that they pulled off the drawing menu when they did the drawing. But the real ones are quite a bit more elaborate than that because you're dealing with very small forces, so your gears have to be very well machined for it to work, and it makes that arrow move, and then that arrow moves against the gauge. So Bourdon gauge, you will encounter them in your life if you have not already. The last one is pressure transducers. I think I have a picture of that. So let's suppose we wanted to make a barometer. We want to measure atmospheric pressure. So there's a couple ways to do it. The smartest would be to go on Amazon and just buy one, but not all of us are smart. Some of us would just take a pot that we find in the kitchen, fill it with water, probably put food coloring in it so you can see what's going on, and then find a glass tube. It's shown there. Put the colored water in the glass tube, fill it all the way up until it's overflowing, and then put your thumb on it, or anything that you have that's big enough to fill the tube. You would invert it, stick it in that pot of water, let go of your thumb and try to get everything out before you break everything. And what you have is a homemade barometer. At this top part, depending on the temperature, there'll be some vapor pressure exerted. So the level of water up here might drop a little bit. At some point, it will equilibrate with the pressure of the atmosphere, and you have a barometer. So if the atmospheric pressure gets bigger means the weather is going to get better. It pushes down on this, which pushes up on this, and the height h will get larger. As the atmospheric pressure goes down, which is indicative of a tornado forming over your trailer, there's less pressure on that. And so that comes down and it goes down to the part that you've labeled on your tube, which is run. And if you follow your own instructions, you would run and watch your trailer go flying away. And hopefully you grab your dog Toto so you don't end up in another episode of The Wizard of Oz. You don't have to use water. You can use oils and mercury. In the olden days, you used to use mercury, and then mercury became terribly dangerous all of a sudden. It is dangerous, but in this application, as long as you're not drinking the stuff, it's probably comparatively safe. But I didn't say that on the video. So any questions on the underlying principle of barometer? They're fundamentally quite simple. Our next tool, 330 to 450, okay. Make sure I'm not wasting your time. I enjoy doing the cartoon stuff. So next one is a piezometer. Piezometer is a fancy name given for a tube that's open at both ends. If you don't want to use the word tube, we go back to Home Depot and we buy a pipe. So a pipe is a tube that's open at both ends until you close in the ends. We shove it into our liquid and we get a pipe that's big enough so the capillary rise doesn't matter. And at the bottom edge of that tube, the height that water or liquid will rise into the tube is proportional to the static pressure in whatever we stuck it into. So if we stick it into a pipe as shown, we're measuring the pressure at that dot in the picture. And that is manifest as water rising in the piezometer. If we want to figure out what the water level is underground at that dot, we can do the same thing. We just drive the tube into the ground, and however high the water rises into the tube is the static pressure. The velocity part is wiped out here of the water in that aquifer. When we put it in aquifer, if we do it for the purpose of measuring pressure, we call it a piezometer. If we're doing it for the purpose of taking water out of that so that we can drink it, we call it a begins with the letter W. Well, thank you very much. There's not much difference between a well and a piezometer. There is some in certain instances, because once we put this hole in the ground, what do you throw down a well? You throw a pump, you throw cables and all sorts of stuff down there. And then what does the well do at midnight on a Saturday on a 3-day weekend? What happens to the pump? It breaks. So always keep a little extra water in the trailer if you're on well water. Or other beverages. Things like beer have a high content of water, so you can live off of beer for a few days if you have to. Our next one is a manometer, which is kind of a hybrid between a barometer and a piezometer. So the idea of a manometer is we stick one end of it into the fluid that we want to measure, and we have the other end in some reference case. In this case, we're showing it as the atmosphere, and then we have a different fluid, the working fluid in the manometer, which is to do the pressure indication for us. The important feature that working fluid has to have is it's got to be something that does not mix readily with the fluid of interest. So if the blue stuff is water, bad choice for working fluid would be alcohol. Why? Because alcohol and water are 100% miscible. They'll mix with each other, and pretty soon you don't have a manometer. You have a mixed liquid drink. And again, Pascal's law is what's being leveraged. And the pressure inside at point 1 is indicated by knowing the distance from point 1 to this side of the working fluid. And then the difference from this side to here is the pressure that's in the blue fluid. So that's Pascal's law. And the thing that's being leveraged is the pressure at this point, at point number 2, moving at the same elevation into the same fluid. It's a continuous stream. Those two pressures are the same. The pressure for the little finger thing is at P2 and point number 2 are the same in that drawing. That's a manometer, and these are actually almost extensively today. In the olden days, the working fluid was mercury. Again, it's been replaced with oils and other things which are environmentally more acceptable. All these devices pretty much are doing a force balance in whatever the column of measurement fluid is to determine what the pressure is. So here's another example of a manometer in a pipe that's running vertical. So imagine it's in the wall, and you read the difference in that height and that height, and we do a force balance on this column of working fluid. We have to know what the stuff is. And from this height, we can infer what the pressure is at that point, which we assume is representative of the pressure inside the pipe. Oh, so transducers are electronic devices that play the same game. Have you had the solids lab yet, where you put the little strain gauges on stuff and bend it and you measure the change in resistance? That's what's going on inside of transducers. There's a strain gauge in it, and the pressure on one side causes it to deform slightly. That changes the resistance in the strain gauge, and you're running that electricity voltage through it, and you measure the change in voltage or the voltage drop, which is proportional to the pressure. And you look up on the manufacturer's specification sheet what each millivolt means when you deform it. Okay, so let's do some examples. Let me read you some examples. I don't think we're going to do them. We were in Ms. Gurley's class. We'd be handing out sheets of paper, and we'd be doing it by hand right now, which is probably a smart way to do it, but I'm too lazy. So hopefully you're all as lazy as I am, okay with this. We actually don't have a choice. So let's go ahead and use some of these ideas that we've just been thrown at you. It's kind of like fire hose. Huh? So we have this tank of water, 10 meters deep. Oh, how convenient. What's the absolute pressure at 10 meters in the tank shown? And we'll just go figure it out using that calculus stuff that we just studied rather than trying to go from memory. Knowing that if we have 1 atmosphere at the free surface and we move 1 atmosphere down in the water, that our absolute pressure is 2 atmospheres at the bottom. So it should be 202 kilopascals. But we'll go ahead and use our problem-solving protocol, because that's part of the class. So we list our known values. We know the liquid's water. We all know that the density of water is 1,000 kilograms per meter cubed. At what temperature? I haven't read the book. So when is water the most dense and still liquid? Sure, you got that in high school chemistry, physics, college chemistry. They don't do anything fun anymore. 4 degrees Celsius. It's just close to freezing is when water is the heaviest, or the densest is water, which is convenient because that means ice floats. If ice sank, it would be awful. If ice sank to the bottom, that would mean the water above it is now insulating it, and slowly the entire planet would freeze into a block of ice. And it would be like being outside all the time. It wouldn't be very conductive to your life. You'd have to go to another planet. So water is 1,000 kilograms per meter cubed. If you multiply by gravitational acceleration, 9,800 meters per meter cubed. Most problem statements are assuming 20 degrees C, so our numbers are going to be a little bit bigger because I want to memorize 4. Our depth is 10 meters, let's give it 8 to 10. And the pressure at the free surface is 101.325 kilopascal. Because we're lazy yet smart, we'll use 101. That should be close enough. And we'll proceed. Our governing or unknowns is what's the pressure at the bottom. That's right here. P at bottom is equal to question mark. That's an indication that we don't know what that is. Our governing equations are simply the hydrostatic pressure equation. To change the pressure, we get minus rho g, or the pressure at B is equal pressure at the surface plus rho g times H. You have to know when we write it that way with a plus sign that H is moving downward in the fluid. If you don't know the direction, write it correctly. You'll have extra minus signs floating around everywhere. Our unknown is PB, and here's how we solve it. We apply the governing equation, insert the numerical values, and we're done. If only they were all this easy. They're not, but this one is. So the pressure at B is 101 kilopascals plus 9,800 newtons per meter squared, multiplied by the 10-meter depth that we just moved down in the fluid. So it's 98,000 newtons per meter squared, which is 101 kilopascals plus 98 kilopascals, which is 199 kilopascals. And we guessed it was going to be what, 202, so we're not bad. Key points we measured down from the surface, and we expressed in some consistent units. The problems may be presented in weird units. It's worth it to convert them to something consistent and use those. That's a classical pressure at the bottom of the vessel. I assure you that any exam you're likely to have from me, there'll be some variation of this. Obviously more complicated because I just told you that it's coming. But the general principles are the same. Here's a second example. Let's suppose we have an oil-water separation tank. It's a fancy way of saying a perfectly good water tank that we got a bunch of oil into. So we'll declare an oil-water separation tank to be our problem. It's open to the air. That's the key point. So we have this layer of oil sitting on top of the layer of water. Why does it do that? Well, the specific gravity of oil in this case is 0.8. The specific gravity of water is 1.0. So oil is fundamentally lighter than water, so it floats on the top. You do that when you make salad dressing and cook at home. Yeah, it does that in real life too. And how long does it stay mixed when you're trying to make a salad in a hurry? Not long at all. Oil is stuff. You know how to make it stay mixed longer? Heat it up. Heat everything up. The emulsion will last slightly. Not long enough to matter. And hot salad dressing on cold lettuce. Yeah. If you want that, just go over to Torchy's. They'll do it for you. Bring the hot lettuce too. Somebody was stupid. They'll put the salads up under the heat pans. They should make them eat it. Okay, so back to our problem. We have this oil there. It's 1 meter thick, sitting on top of 2 meters of water in a tank. And for some reason, you're more curious what the pressure is at the bottom of the tank. So in this case, we're going to be moving down from 2 fluids. So essentially, we have 2 of the prior problems in a row or in series. We'll figure out what the pressure is at the oil-water interface, and then from there, we can figure out what the pressure is at the bottom of the column of water. So here's what we know. We know the water has specific gravity of 1. Its density is 9,800 newtons per cubic meter. We have oil with specific gravity of 0.8. Its specific weight is 9,800 multiplied by 0.8 newtons per meter cubed. We have the depth into the oil of 1 meter, depth into the water of 2 meters. We know that we're starting at 100 kilopascals at the surface of the oil. So our governing equations is the same one as before. PB is equal to PA plus specific weight times the change downward into the to whatever layer we're interested in. That's Pascal's law. And unknown is P2, and technically we don't know what it is. So our solution would be to apply the governing equation in the oil phase to find the value of P1. And then from that, apply the governing equation in the water phase to find the value of P2. So let's go ahead and do that. Again, I'm glad I'm not writing this on the board. We would be in a cloud of chalk dust by now. So P1 is equal to the initial pressure at the top, which was 100 kilopascals, plus rho oil times G delta H, which is equal to P0 plus 9,800 times 0.8 times 1 or in numbers, 100 times 10 to the 3 plus 7.84 times 10 to the 3 for a total of 107.84 kilopascals at the oil-water interface. We'll use that value as our new starting point for moving down in the water. So our pressure at point 2 is equal to pressure at point 1 plus the added pressure moving into the water. So 107.84 kilopascals plus 9,800 meters cubed by 2 meters. 7.84 plus 19.6 kilopascals, both cases, for a total of 127.44 kilopascals. At absolute, because I guess that's interesting. Yeah, it is absolute. If we were at the atmosphere and it was gauge pressure, we would have started with 0. That's an absolute pressure. So what we had here in way of discussion, we had 2 liquids that start at the top and work down. We used a specific gravity to relate the specific weight of oil to water. That's the value of specific gravity. Because I did this by hand, I didn't do that calculation until I was absolutely forced to. Using a calculator is just asking to make a mistake. And if you don't make mistakes with money, there's no point in making mistakes with engineering calculation, because that usually leads to loss of money. And then remember, we have to use the correct specific weight for whatever fluid we're in. So if we're moving down in water and we use the oil specific weight, we're wrong. If we were interested in the gauge pressure, we actually could subtract off what the original pressure was, that 100 kilopascals, and find out that moving down 1 meter of oil, 2 meters of water, we get about 30 kilopascals increased pressure. And now we get to the famous manometer example. If you read your book, there's probably 3 pages of manometer. Back in the olden days, this took weeks to get through. Before the advent of the calculator, the computations involved were kind of annoying. So here we have 2 pipes, pipe A and pipe B. Pipe A, there's presumably water. Pipe B has water, and we're using this elaborate bendy tube system to figure out what the difference in pressure is between the 2 pipes. So in the year 2022, this would be a monumentally stupid way to measure differential pressure. It's the only thing you could think of, then go for it. But if you presented this to your manager and these differential pressures involved a lot of money, they would laugh at you. Why don't you take the rest of your life to figure out what you want to do, or come back with something a little bit more sophisticated? Our chemical engineering friends would laugh at us, but we'll just do this for a fluids problem. In these 2 legs of this elaborate bendy thing, originally it was probably just one U-tube, and what happened is somebody ran over it with a forklift, still welded up. We have mercury in this leg here, and in this U-shaped part here, and then we have oil separating the 2 mercuries. I don't actually know why you would have oil doing that, but so be it. That's what it is. So we're given that the pipe fluids are water, oil, and mercury. We know that the specific gravity of mercury is 13.6. How do we know that? Google, good. The specific gravity of oil is 8/10. Same source, if nothing else. Google will work for that. Our governing equations are essentially the hydrostatic pressure equation, slightly modified to handle different fluids. So the pressure at position 2, in any case, is equal to what you start at, plus the sum of all the downward increases in pressure, minus the sum of all the upward changes in pressure. And you see these I subscripts keeping track of what fluid is in. Let's see how it manifests. The unknown is the change in pressure between the 2. Solution would be to apply the equation. And here it is just laid out. I'll go through this.
potential too. And here we have our system, and we've gone to some way of indicating the different fluids. The picture, like to implement the changes in pressure using that algebra stuff, and then the various pressure equations in. Don't put numbers in stuff. And formulate that whole set of equations. We have the individual pressure equations. You know that's got to use the total change to discover that a lot of times pressure spells out. Also going to be a PA to replace each of the parentheses terms by their hydrostatic pressure equation representation. So there's the PA minus PC term, PC minus P0, PD, and so forth. All right, makes sense? So those are all just replacements for each of these things that are shown here is canceled out, but we're still keeping track of what's in the parentheses. And then write down the individual elevation changes. And now we will start to put our densities in. So we have water, mercury, oil, water, or mercury, water.
Group all of each kind together. So all the waters you group together, all the mercuries group together, all the oils. The pluses and minuses will take care of themselves at this point. And finally, we express everything in terms of the specific weight of water. And we come up with a differential pressure, in this case of 3.7 pounds per inch squared. If you were to try to do it one at a time and actually put numbers in at the beginning, eventually you get there, but you would probably give up. I know I would. So in this case, we illustrated use of different fluids and took advantage of algebra. We'll stop here for now. We'll pick up with example 4 next time, although I think you have a homework assignment on example 4, so look at it and have a great weekend. Thank you for your patience and attention. And I warned you we wouldn't get to the end today, so that's fine. You're all free to go. You've done very well.